maybe let's start there.
Okay. So we continue from last time. So by the way, let me make one announcement that the notes of these 5 lectures will be put on my personal website later on. My personal website can be found from University of Chicago, and just click the department and find my personal website, and then the notes or the link to the notes will be put there. Okay, so. Yeah. Okay, so last time we were focused on the proof of this theorem. So let me write this theorem here. So assume M has 2 layers. Each layer is a tree. And number of edges, bonds, let's say, between the 2 layers equals rho. Then we can cut M into elementary components such that the number of 3 threes is bigger than a constant times rho, and then it's also bigger than a large number of 4. Okay, so let us focus on the proof of this theorem. And last time we also introduced this first algorithm, like a first main algorithm, which is called up. Which is described as following. So basically each time we choose a lowest degree 3 atom, say n, and let Sn be the set of descendants of n. Descendants means you start from n and keep going down, keep taking a child, and we cut atoms in Sn from top to bottom. In other words, you first cut n, and then you cut the child of n and the 2 child. You know, if there are 2 children, and if there are one child, you cut a child of n, and then child of n, and so on. And then if there exists degree 2, cut it. Otherwise, find the next, choose the next lowest degree 3 atom and repeat. Okay, so last time we saw one example of this algorithm. We can look at another example just to get ourselves familiar with this algorithm. So another example, let's say let's see if you have this. Okay, so this is a molecule of 4 atoms, and then it actually has a cycle. And basically what we do here is that and draw one by one. Okay. So we start by choosing in the beginning there is no degree 3, so we choose the lowest degree 4. If no degree 3, then choose lowest degree 4. And here we also mentioned that if there is possibility of 3, then cut it. Okay, so for example, in the beginning, we start with this one. This one we cut it because there is no degree 3, which is lowest degree 4. After we cut it, we get a 1 degree 4 component plus what remains is and then these are fixed ends, so let's just not draw it. So let's say these are just degree 3. Okay. And then we choose next choose a lowest degree 3, and both this and this are lowest degree 3. We can choose either one. So let's say we get let's say we cut one on the left, so we'll just get this. Okay. Now since we cut this atom as free, then we're having a fixed end here. So do not draw this edge here, and do not draw this edge here. Okay, and then we are left with this example. And now what is lowest degree 3? This one is lowest degree 3. And this one is degree 3, but it's not lowest, so this one is lowest. And we should cut this one, but then notice that this one now belongs to a 3, we're both add the degree 3. So we simply cut them as together, and then we get so this is what the algorithm looks like. And last time, remember, we also stated, the two properties of this algorithm. So let's just review it here. That this algorithm never produces the kind of components that we do not allow. Never produces these kind of components. In fact, what happens in the execution of this algorithm is that at any time the fixed ends at atoms in. Remember, at each time we're having this atom n, which is a lowest degree 3 atom, and then this Sn is a set of descendants of the atom n. And then the fixed, for each atom in the set Sn minus n, the fixed ends at this atom must be from above. And the fixed ends at atoms n union the complement of Sn must be from below. Okay, so let me illustrate this fact, and once we have this fact, then obviously, like for each atom, either the fixed ends are only from above, or the fixed ends are only from below. Then we conclude that we can never have things like this, or have fixed ends both from above and from below. Okay? Let me show you what this means. Basically, let's say at any time you choose a atom n, so this atom n, at any time of the algorithm. Remember, if you read the algorithm, you choose a lowest degree 3 atom and call it n. So this is n. And then this Sn is a set of descendants of n. So what are the Sn? Sn are like this. Okay, you may have this, fine, and then you may have so this set, let me put it in the box. This set is Sn. Okay? So remember, at the time we choose this atom n is the lowest. I think I draw it wrong, so I should have only one. Let me draw it again. So this is n, and this has this. Now we have okay, so this will be Sn. Okay, so this will be a fixed end. Okay, so remember that n is a lowest degree 3 atom, so which means everything below n, so everything in Sn minus n, is degree 4, which means it has no fixed end at all. Okay, so that's what happens when we choose this atom n, and then we are cutting the atoms in Sn, cutting the atom in this box, but we're going in the order. We're going from top to bottom. We're first cutting n, and then cutting the child of n, and the child of n, the child of n, and keep cutting the child's the children, the descendants in this way. Then what happens here is that when we cut anything, let's say if you have this, when we cut anything, let's say when we cut n, okay, so it introduces a fixed end, it introduces a fixed end, at its child, but this fixed end is only from above, okay? And again, we cut the next one, so introduce 2 fixed ends, but then again, they're only from above. So they are only from above. Since in the beginning, the Sn has no fixed end from below, then in the whole process, we'll only introduce a fixed end from above. We can never have any fixed end from below in this set Sn. Okay, so let's recover this picture. Let's say this. So this means that the fixed ends at the atom, in Sn minus n must be from above. At n you have fixed end below, but otherwise, at everything else, you must have fixed end only from above. This is one thing. And now what happens about those atoms outside Sn? It's also fine, because the thing is that you may have, edges, connecting the atoms in Sn to the atoms outside of Sn. There is an atom here. There's an atom here. But then these edges must be going up if you view from this point in Sn, because the child of Sn is still in Sn. By definition, Sn is the descendant. So if it's connected to something outside of Sn, it must be the parent. And then you may have other parent, other child. Doesn't matter. The thing is that since you're only cutting the atoms in Sn, so if you cut one atom in Sn, so let's say at some point, you're cutting one atom in Sn, you're going to introduce fixed ends outside of Sn. So this is SnC. You're going to introduce a fixed end outside of Sn, but this fixed end must from below, because this is a child. The thing you cut is a child of the atom you have in question, and then this introduces fixed ends that can only be from below. Okay, so this is a monotonicity kind of in the setting of the algorithm up, and it tells us that any fixed end inside Sn must be from above, and any fixed end outside of Sn must from below. And in either case, you cannot have this forbidden structure. Okay, so this is the first thing, that it never produces forbidden structure. And second thing is easier, that it produces only 1 degree 4 components, for each component of the original graph, which is for each component of M, it contains 1 and only 1 degree 4. And this is also easy because in the beginning you must have degree 4. In the beginning there is no degree 3 and you must choose degree 4. But once after you make your first cut, then in the rest of the whole process, you are going to have something that is degree 3. Because if you cut anything at all, you are going to produce a fixed end. Okay, so if you cut this, you are going to produce a fixed end here, and then if you further cut this, you're going to produce a fixed end at other places. So you always have a fixed end, so you always have degree 3 atom. And by the definition of the algorithm, if you have any degree 3 atom at all, you will not have a degree 4. You will not have this. Okay, here because. So this tells us that this up algorithm, it already kind of guarantees 2 of the 3 properties. First, it preserves the monotonicity in the sense that it doesn't produce these bad structures. And second, it minimizes the number of degree 4s you may choose just by allowing 1 for each component. And of course, in the case where the M is kinetic, you only have 1 degree 4 no matter what, and this is negligible. So the only thing is that we showed last time that this may not always maximize the number of 3s, and it's something that we want to solve. Okay, so today let me start with a simple case. So it turns out there is a one simple case where you can just do a small modification or small specification of the algorithm up, and that will be enough to guarantee a number of 3, and that is theorem. Case 1. So this is a proof of the first case of the theorem here. That is, recall, we just want to prove that you always can find a good sequence cutting these into elementary components. Okay, case 1. So let lambda be the number of atoms in the lower layer. We call this NB. So this, let me just mount this lower layer. We call it down layer. Basically, there has 2 layers, one up and one down. So number of atoms in the lower layer that are connected to 2 atoms in MU, which is the upper layer. Then, if lambda is bigger than, let's say, 10 to the minus 4 times rho, theorem 1 is true. The theorem is theorem 1. Let's call it theorem 1 anyway. This is really the okay. So that would be the number of atoms that are connected to two atoms in the upper layer. So it has any atom in the lower layer. It can have only two parents, and now if both of its parents are in the upper layer, okay. So this is what is contained in this lambda. Usually we call these two connections. Well, these two connections. And this case 1 tells us if the number of two connections is big, is not very small, then we are done. Okay? So let's show you example. What is the case when I have, let's say, many two connections. So let's let me draw a different one. Okay, so let's look at the picture. So this is like kind of this on the upper level you have a chain, like a zigzag chain going up, down, up, down, up, down, up, down, and on the lower level you have a zigzag chain going down, up, down, up, down, up, down, up. Okay, and then you see you're having these blue edges are the the UD connection, the connection between the up layer and the down layer. Okay, now you see that, for example, each of these atoms is a two connection, okay, because it has two edges connected to the top layer. Okay, so if you think of this chain continuous, then these you have as many two layers as you want, and the case 1 tells us that this case is good. That we are gaining the number of the number of 3's, like as many as the number of two connections. Okay, so in this case what we do? So proof of case 1. I'll keep the picture here because we'll do operations on it. It is very simple. We perform an ARC algorithm in MU only. Okay, so just so we imagine MD doesn't exist, we just apply our ARC algorithm in MU, except when an atom N in MU forms a 3-3 with an atom in the lower layer ND, this is MU, this is ND, in which case we cut this 3-3. Well, okay, so it's really just that simple. Well, in our paper we named it, we gave it another name. This is a two connection ARC, because in the real case it contains a few other cases that when you do kind of slight variations, but essentially this is just a special case of ARC. Okay? And in this case, we can show that essentially each two connection is indeed corresponding to a gain, and then the number of gains is bigger than the number of two connections, and then we're good. So let's see, let's demonstrate from this picture why it's the case. Okay, so essentially, the idea is that for each two connections, so let's draw another picture here. So in this each two connection, let's say N belong to ND, must belong to a 3-3. Okay? Once this is true, then of course, since the number of two connections is lambda, lambda is bigger than constant times rho, then we get that the number of 3-3 is bigger than constant times rho. And then of course, since number 4 is just 1, it's obvious the second inequality is also true, and then we complete the proof of theorem in this case. Okay? So now why is this true? Why is N must belong to a degree to a 3 component? Let's just look at this picture and let's try to carry out the process like in the ARC algorithm. Well, the first thing we cut the lowest. So as I said in the beginning, there is no degree 3. We cut the lowest degree 4, which is this one. Okay. You see, once we cut this one, so let me remove the. We get this. Okay. So this thing becomes degree 3, but as I said, I'm only caring about the cutting and U, so we ignore this for now. Okay, so now this becomes degree 3. We cut this. So this is now the lowest degree 3. We cut this. Okay, so now we cut this. What happens here is that once we cut this, now this atom becomes degree 3. And in the meantime, this atom, this two connection atom, is still degree 3. And then we're in the case where we have a 3-3. Okay, this M in the top layer forms a 3-3 with something in the bottom layer, which is this one. And we can just cut this. Okay, and we get one 3-3. You see, we already get one 3-3 here. Okay, so see, remember this atom we just showed, it becomes part of the 3-3. Okay, and next, let's look at this atom. This is lower degree 3. We should cut it. And once we cut it, again, this atom becomes degree 3, and this box atom is still degree 3, and then we get another 3. And then we remove it. And then you can keep going on. This is below degree 3. You cut it. This becomes degree 3. This becomes degree 3. And again, we cut them together. Then we get. And then if the chain continues, we keep doing this, and then you see that each of these two connection atoms, they always belong to a 3-3 component, and so the number of 3-3 components we get is as many as the number of 2 connections, and then we have. Okay? So the proof actually is not how to prove it. Basically, we can even do an abstract proof. Let's say you have a 2 connection atom N here that's connected, has 2 parents. This is M1, M2. This is MU. This is MD. Okay, so since in this algorithm here, we're first cutting the atoms in MU. So see, we are just cutting, let's say, the atoms M1 and M2. The thing is that, let's say we've cut M1 before M2. After we cut M1 and before we cut M2, this N will become degree 3. Okay? After we cut N1, before we cut N2, this N will become degree 3 because it already has one leg, and one edge being replaced by a fixed end. If you want, you can draw the fixed end here. Okay, so let's say because this, there is M1 here that is cut, so then becomes fixed. Now, at the time you would cut M2, remember you would cut M2. Let's say, if you ignore the MD, if you're just working MU, apply the algorithm to MU, then you will be cutting this M2 at some point. And at this point, this M2 must have degree 3 because it cannot be degree 4 because, we know the MU is a tree, so only the first step you have degree 4, and from after you never have degree 4. So this M2 has to be degree 3 when it's cut. So this has degree 3. But remember that even after M1 is cut, this N atom has always been degree 3. And then whenever you would cut M2 in this algorithm up, this will have degree 3 and this N have degree 3, and then by this except sentence, you know that you must be cutting this M2 and N as a 3-3. Okay, and this argument applies for each single 2 connection atoms, and then you conclude that this must belong to a 3-3 component for each such atom. And then if the number of 2 connection atoms is large, then we are good. Okay, any questions? Okay, so this already counts for the first case. The first case we have many 2 connections, and from now on, given the first case, here is this. Well, this 10^4 is a very, very small molecule, and in fact, in practice, we'll just assume lambda is 0. For simplicity, so lambda equals 0 means there is no atom in lower layer that is connected to 2 atoms in upper layer. So means no 2 connection in MB. And of course, by symmetry, let us also assume that no-to connection in MU. Otherwise, we can define an algorithm we call down, completely due to the up algorithm that we apply to the ND. Okay, so from now on, let us make this simplification, and then we'll still have 2 cases to consider. Okay, so let's summarize. I'll assume that ND is a tree, MU is a tree, no two connections, which means each atom has at most one edge, at most one bond connecting to the opposite side, and then the number of UD connections. Now let's focus on this here. What do we do here? So to proceed, we need to make some further observations regarding this algorithm up. So we already have some familiarity with this algorithm. So you know it preserves the preserve the monotonicity. It avoids this back component degree 4. And then, while it doesn't necessarily maximize the number of gains in the 3 components, but in some cases it does. So let me now point out another important case where indeed the algorithm up can guarantee a kind of big enough gain in terms of degree 3 suites. Let's make one more observation. First, it can be applied. So when we apply this up algorithm, initially in the beginning, we assume this whole molecule has no fixed end. In the beginning, the whole molecule has no fixed end. But then, even if we have already applied some cutting algorithm to the molecule, so that our molecule now may have some fixed end, then we can still apply the up algorithm as long as it can be applied to a molecule with fixed ends, as long as there is no fixed end from above. Okay, so this is important observation. So basically, if you have a molecule with some fixed ends, as long as these fixed ends are all from below, you can still apply the up algorithm. And the reason is that remember this important property that in the up algorithm, this is n, and this is a fixed end, and then we have a number of things. Okay, so this is n, and then you may have something like this. This outside of Sn. Okay, so the key thing is that you see, in the previous discussion of our algorithm, we're assuming that there is no fixed end kind of outside the picture, but in the whole picture. But it may be possible that if there are fixed ends like this, if there are fixed ends kind of from below, Okay, so if the whole molecule has no fixed ends from above, the only fixed ends are from below, then the same up algorithm applies in the same way because remember our invariant property says that the outside of Sn, so this is, you may have more, of course you may have more, but outside of Sn, there is no fixed ends from above, but even if you add more fixed ends from below, it doesn't destroy this problem. Okay? On the other hand, this Sn, by definition, it will have no fixed ends from below because in the beginning, when you choose n, this Sn will have degree 4 because it has no fixed end at all. Okay, so this is a kind of small kind of observation that we can apply this Sn to a kind of a partial molecule where it already contains some fixed ends as long as there is no fixed end from above. So this you can easily verify. This is the first kind of property, and the second property is the most important one. Second, let me write it here.
Excuse me.
Yes.
If there is some fixed ends from above, there will appear some
Bad.
So both have fixed ends as up and
Yes,
down.
yes. So that's why we are requiring no fixed end from above. Suppose M is a tree, has no fixed end from above. And the set of degree 3 atoms, so let me just say, and degree 3 atoms are separated by degree 4 atoms, then you can gain large power by applying up. Okay, so this is a non-precise statement, so let me show you what this means. Let's say you have a molecule M, which is a tree. It may have some fixed ends, but again, no fixed ends from above. And then we consider those atoms in N. It may have degree 3, may have degree 4. Let's say we ignore degree 2. Degree 2 will be cut, so no matter what. Okay, so let's say we have degree 3 and degree 4. And then we look at the possibilities are when the degree 3s are kind of stick together or when degree 3s are separated by degree 4. So, bad case. Let's say you have a chain. Just for simplicity, let's say we have a chain, the M is a chain. Okay, so let's say we have this, and then we have, okay, so let's say this is a fixed end here. It's fixed end here, fixed end here, fixed end here, fixed end here. So this is a bad case because every one of these atoms is degree 3. So degree 3 are not separated by degree 4. And if you just draw the degrees, it will be schematic. It will be like this. Okay, something like this. And this is a bad case because you don't get enough 3 3s. And this is very clear. You have to start from the bottom. Start from the bottom, choose the lower degree 3, and this is lower degree 3, and this belongs to these belong to a 3 3. In the beginning, you should cut this. Okay, so because this is 3 3, and once you cut this thing becomes degree 2. So on the schematic picture, you cut this, and this becomes degree 2. And once this becomes degree 2, you are forced to cut it, and this again has degree 2. You cut this, and this again has degree 2. And then again, you're forced to cut it, and again, this has degree 2. So you cut this, and this is degree 2, and then you cut this. Okay, so you see, for the whole long chain, as long as it may be, you only get one gain from the 3-3 component. In this case, long chain of degree 3 implies only 1. And this is certainly not enough, given how long the chain is. Now, this is when degree 3s are stick together. Now, what is a good case? The good case is when you have again a long chain. Draw it here. Okay, so let's say you have this. Say you have this fixed end, this fixed end, this fixed end, this fixed end. Okay, so this is degree 3 and this is degree 4. And this degree 3, this degree 4, 3, 4, 3. That's when the degree 3s are separated by degree 4s. Let's just say, schematically you have a 3, 4, 3, 4, 3, 4, 3. Why is this good? Okay, again you apply up, so choose the lowest degree 3, you cut it. Okay, so it doesn't cause anything, but then, okay, you see you're having a fixed end here. So in other words, on the right, on the schematic picture, you remove this degree 3, and this degree 4 becomes degree 3. And now you get your first 3-3 component. Now this is a 3, 3, and this is 3, 3. So get 1, 3, 3, fine. You remove it. So after you remove it, this degree 4 becomes 3, 3. So having this. Okay, so in this picture, you remove this, and we get a fixed end here. Now you see, you get a second 3, 3, which is this one and this one. Okay, and in the picture is this one and this one. And then you can get your, remove it again, get another 3, 3. And in the picture here, you can cut these two together, get a good component. And then you have a next 3, 3 in this picture. And get yet another 3, 3. So you see, this is in sharp contrast with the bad case. In the bad case, you just have the first component being 3, 3, and everything else being degree 2, which is not good. And then here, since you have these degree 4s in between, then you're going to have a number of sequence, or each thing in the sequence is a 3, 3, which is good. Okay, so this is the kind of the key thing, you know, in this lemma, that when the degree 3s are separated by degree 4, you are good, you are gaining a lot heuristically. If not, you're not necessarily gaining a lot. So let me make the statement more precise. Let X be the set of degree 3 atoms, mu be the number of components of X, and specifically notice that when we talk about components of X, we mean those components in the same component if they are connected only within X, and we don't count connection with, via other atoms not in X, we're only counting X. So that mu be the number of components of X, then we can apply up get the number of 3 3s bigger than, let's say, mu over 10. Okay. again, we don't, as long as we're applying up, we don't need to worry about the loss of degree 4s because this will always be tiny. The only thing we need to get enough 3s, and this is the result. So if the mu is number of components, so in the bad case, all the degree 3s are still together, so mu is 1 because all the degree 3s are connected to each other in X. But in that case, if you have a if you have 3, so mu is 1. But in that case, if you have a 3 degree 3s separated, then the mu is the length of the chain divided by 2, which is very large. Okay, so this is the kind of the two cases. The bad case, when the 3 atoms are stick together, then we cannot gain. Otherwise, if the degree 3 atoms are separated by degree 4 atoms, then we can gain, and the gain, quantitatively, this gain is exactly the number of components of the set of degree 3 atoms. Okay, so this case, each degree 3 is a separate component by itself. If you consider the subgraph kind of formed by subgraph X formed by the degree 3 atoms. Okay, any questions? Okay, so this is kind of the second key lemma. So the proof of this lemma, in the general case where M is a tree, is a little bit technical, so we'll not present the full proof, but we can see at least the case where M is a kind of monotonic chain, as you are having here. And first observation, we erase it. Proof. Monotonic chain means a chain formed by, the something and taking child, and taking the child, taking child, taking child, and things like this. Okay, so let's formally draw a chain like this, and then let's indicate the degree 3 atoms by these yellow segments. There's a keep going on. Remember that everything here is degree 3. Degree 3, and here everything in Y for degree is 4. 4. Okay, so in this case we do the up algorithm. So we start with the lowest degree 3, which is, for example, this one, and we just all the way going from bottom to top. In the simplified case, N is monotonic chain, so we'll never have any, bad, disallowed degree 2 structure. So we can ignore that. And then let's see. We go from bottom. We have a chain of degree 3. Okay. We have a chain of degree 3. So let's look at what happens here in this part. So we have a chain of degree 3s. So we have a 3. You get a 4. And you get maybe a number of 4s. You get next to this picture. Okay. The thing is that if this chain of degree 3 has at least 2 degree 3s, you already get a 3-3, and we are good. This our goal is to find 1 3-3 for each kinetic component, for each segment of degree 3s, right? So if you have a 2 degree 3, then we already get 1 3-3. Okay? So let's say we don't have a 2 degree 3. Let's say we only have 1 degree 3. We say we have 1 degree 3 like this. Okay? And then we cut this degree 3. We cut this degree 3, that means this degree 4 becomes degree 3. Okay? And then we cut this degree 3, and then 3, and then degree 4, 4, let's say again, 4, 4, and then we have a 3. Okay? So let's say we cut this. We cut this degree 3, and this becomes a 3. You see, this is the rule. If you cut something, then the adjacent one becomes 1 fewer degree. And then we have this degree 3. Again, we cut this. And the degree 3 is shifted here. And then we cut this. It's shifted here. And then we cut this. It's shifted here. And then we get a 3. Okay? So you see, when you kind of go through one segment of degree 3 and one segment of degree 4, and no matter how long these segments are, you always get at least one good component series. So if you just formally go through these segments from bottom to top, when you go through, let's say, this part, you're getting one good component. When it goes to the next part, you're getting one good component. When it goes to the next part, getting one good component, and so on. So then the number of good components you get is at least as many as the number of segments here, which is the number of components of the set X. So see, this is an important thing. So you are not gaining 1 degree 3 per atom. You're not getting good components of degree 3 per atom. We're getting one good component per kinetic component, per segment. Okay? Oh, this is special case. And the general case is a little bit subtle, but I think this should already demonstrate my idea. In the general case, you have branchings of the trees. You need to choose a correct kind of branch to work on. But okay, so this is not a big problem, just a technical. Okay, so I think we are. I think it's good to pause here to stop for the first half. So basically, let's summarize. So we have, using the algorithm up, we're already done with the case of many two connections. And from now, we assume there is no two connections. And then we made this key observation that if you have a tree where the degree 3 atoms are separated by degree 4, which means this set X has many kinetic components, then we're also good. We're also gaining, as many as the number of components. And then using this fact, we're going to, for the molecule that has no two connections, we're going to state a key dichotomy that we divide our problem into this final kind of two cases. The first case, we're going to use disregard, and in the second case, we really need to introduce a new component that is beyond the algorithm up that we'll talk about in the second half.
Let's assume like half an hour. 但如果有问题的话，就直接讲台上。
The final part of the proof. So half of the proof will rely on this lemma 1, and this other half will see new methods. Okay, so assume in theorem 1, so MU and D each is a tree. No two connections. Number of connections, or we call UD connections. Well, the picture is that if you have, sometimes we may not even need to draw this interface between the layers if it's clear enough. Let's say you have a chain, just in the simplest case. Okay, let's see, we have this. So we have these, UD connections, So we're not supposed to have two connections like this. So we have one connection or single connections. So each atom has only one connection to the other side. And let's say we'll draw two examples, and these correspond to two cases in our dichotomy. So case one, let's draw this. We can draw complete the rest. No, skip one. So. This we call the case, maybe case 2. We already said case 1 is a two connection case. Let's say we draw another one. So okay, so we'll see what's the difference between these two cases. Essentially, you consider those atoms. So if you want, we can still draw the interface, just in case if you interface, and this will be interface. So if you look at those atoms, let's say in the top layer, that has one connection, no two connections or any connection, the one connection, those atoms that has one connections, in the case 2, these atoms are disconnected, right? So these atoms are not connected to each other because they are separated by the other atoms. And in case 3, everyone in the top has a one connection. So these, in particular, these atoms are connected to each other. Okay, and then we introduce this dichotomy. That X is a subset of MU with a set of atoms in MU that are connected to an atom in ND by a bond, are connected to, let me say, to one atom and only one atom. So this is the set of X. There's the set of, let's say in the upper layer. In our case, it's symmetric, but in the actual case, there is a little bit asymmetry, but that's fine. So let's say look at the top layer. So X is a set of atoms in top layer that are connected directly to the bottom layer, okay, by a bond. So dichotomy is that we have two cases. So let mu, number of components, of the set X. So dichotomy is well, mu less than 10 to the minus 2 times rho. Again, remember rho is our goal. The goal is the goal we want to reach, the number of series we want to reach. Or, so let's say mu bigger than this is the two cases, and these correspond to case 2. And these correspond to case 3. Again, we are already having no two connections, otherwise we're in case 1. Okay, so it turns out that in case 2, we can apply easy argument using this lemma 1, using this this x. Well, this x will be the same x, provided we cut the bottom layer, we'll see. And in case 3, we need to introduce something completely new that is not a variant of the up algorithm. Okay, so in that case, we'll kind of do something else. Okay, so let's say case 2. What we do in case 2 is that we'll cut MD, the whole set MD as 3. So let's say we shouldn't worry about what we do with MD, because we can always cut it kind of, if we don't aim to achieve a gain, we can always cut it using the dual algorithm up to avoid any loss. Let me see that. Let me say that. Avoid these degree 4 components, and so we don't need to gain from MD, and then we can do a kind of naive method using up or down. Using up or its dual. Doesn't matter. Okay? So then what happens is that if you cut everything in MD, then those atoms in MU will have different degrees because they will have fixed ends there. Now that after cutting MD, we'll have fixed ends in MU. However, since MU is always above MD, these fixed ends are always from below. So this is a good thing, because remember, we can apply the up algorithm to any molecule with no fixed ends from above, and this is what happens with MU. MU has fixed ends but only from below because they're coming from MD. If you cut, if you cut this, you create a fixed end here, but this is a fixed end from below. So let's draw this picture out in case 2. How is this? Unfortunately, in the ball, I cannot copy and paste. But, So we cut everything MD. We can just, again, try to go from bottom to top, so it doesn't matter. So let's say we cut this. And then let's draw out there is a fixed n here. Okay, and then we can cut this. Fine. We can cut this. And there is also a fixed n here. And we cut this. Doesn't affect this cutting this doesn't affect the top layer, but then we cut this, again introduce another fixed n. After this, we are having this mu. Now it's a tree. It's still a tree, and then it has a number of fixed ends from below. And then notice that has no degree 2 atoms. Basically for any atom, how many edges are affected, how many degrees it are affected. If something has no connection to MD, like this guy has no connection to MD, then initially it's degree 4, now it's still degree 4. This is still degree 4. Now if it has one connection with MD, then initially degree 4, now it has one fixed n, now it becomes degree 3. If something was to have 2 connections to MD, then it would have become degree 2, but such atom does not exist, so there is no degree 2. Okay? And those in X will have degree 3, and those not in X will have degree 4. Okay. And now, here's the time to use our case 2 assumption. Mu is the number of components on X, and that is big. Okay? So, now we can verify that this mu satisfies all the assumptions we want. So mu is a tree. It's a tree. It has no fixed end from above, every fixed end from below. And let X be a set of degree 3 atoms. Here X is precisely a set of degree 3 atoms. And then the number of components of X is mu, and mu is bigger than this number. Okay? By lemma 1. You can apply a variant of up. Again, in our paper, since this will involve several other kind of technical cases, we are calling this, giving it a new name, 3-component up. So again, the goal of the use of this is to we can get, let's say, number 4 is still 1. And number 3 threes bigger than mu over 10, which is bigger than and then we are done, because we already get number 3 threes bigger than constant times rho, and it's clearly bigger, much bigger than the number degree 4s, and we are done. Okay, so this is case 2, which is really simple, given this lemma 1. Of course, lemma 1, we already see the proof in the case of a chain, but in general, there are multiple chains forming a tree. You just need to essentially work with every chain. Okay, so this is case 2. Now we are finally left with case 3, where mu is very small. So let me now we forget this lemma, so we no longer need to use it. In case 3, so let me first write down the algorithm. I will show you what it means. It has one key new ingredient. I'll explain what it is. We do the following. Remember this set X. we still have the set X, except that now we haven't cut MB, so X is still the set of atoms that are connected to MB. Each time, choose a lowest atom in X. Choose only in X. I mean, of course, or lowest degree 3 atom called N and cut so let's call it N. Let's say, and let be the set of okay. So I'll write down everything and then I'll explain. First step. Okay, let's go over what this means. Okay, so at each time we are choosing lowest atom in X. So specifically, we notice that this step is almost like the most naive algorithm we said before. Even if this lowest atom in X has degree 4, we still allow to choose it. So this creates a problem that we may have a lot of degree 4s, but we'll see this in the end. Okay, so each time we choose a lowest atom in X, if there is nothing in X, then we choose lowest degree 3 atom as usual. We call it N and define this as N to be the cell descendants in N. So let me have this picture. Let's draw a general picture here, and then we'll see specific examples. Okay, so let's see. You have a point, this is N, and then N has a bunch of, like descendants. So S and B is cell descendant of N in MU. Doing things like this. M is a tree, so it has no branchings and things like this, okay? And then, N has a N, and this, and we have this, whatever, doesn't matter. Okay, then the thing is that N is going to have one connection. Okay, in here. And you see, since N is the lowest atom in X, which means that this thing in Sn This is Sn. Everything else in Sn has no connections with the lower layer. Only n has one connection. Okay. So then we keep cutting. Basically, we cut x, and then we cut this. Keep cutting. Keep cutting this. The point is that when we cut x, so usually each time we cut the highest atom in Sn. So here we cut n, and then we may cut the next one. Okay. So the point here is that if we cut n, then it may affect. So this NU, this NB, it may affect the degree of atoms in NB. Because if we cut this, then the degree of this gets reduced by 1. Okay? So initially everything in NB has degree 4, but as you go, go through this process, you're cutting these atoms, and the degrees of atoms in NB may decrease, may become from 4 to 3. Okay? And then at some point, you may suddenly find that you are having a 3-3 component in NB. And just for technical reasons, we are also counting the kind of the 3-4-3, which means a degree 3 connect degree 4 connect degree 3, or if you want to draw it like this, then you have a fixed end here, a fixed end here, a fixed end here. Okay, so this is just for technical reasons. We're also including a 3-4-3. It plays essentially the same role as a 3-3. Okay, so at some point you may suddenly find yourself, okay, so your MD now have a 3-3 or 3-4-3. Now, as long as you find anything there, you immediately switch to MD and you cut that atom. So we'll show you examples. And cut that component 3-3 or 3-4-3. Okay. And then after you finish cutting MD, so there is no more 3-3 or 3-4-3, then you go back to MU and you cut the next highest atom in Sn, and you keep going until everything in Sn is cut, and then you choose the next M and so on. Okay, so this is a complicated process, but essentially it can be divided into two parts. In MU, it's essentially kind of naive up, because each time we just choose the lowest. Okay, so this is like in MU plus a greedy algorithm and greedy algorithm means as long as you have something that can gain, this is something you can gain, and this is something that's also you can gain eventually, then immediately remove it. You don't even think of how this will affect the rest of the molecule. You just remove it. Like when you see anything good, you just take immediately. So this is essentially greedy algorithm MD, and what is naive in MD? It's a combination of these two. In naive thing in the up layer, you keep choosing the lowest, and in the a greedy algorithm MD, you gain something as long as you see a chance to do it. Okay, and then let me show you a few examples. First, let me show you the example of a greedy algorithm. How do we execute this MD? How this thing, how this thing works out. So greedy algorithm. Let's say an example is like this. Let's say if you have imagine this interface, and then you're having something. Okay. Let me draw some pictures. Number of fixed ends here. There's a cross here, cross here, there's a cross here. So this is the molecule in terms of degree. It's slightly easier to draw this in terms of degree. This is N. This is 4. So this is a schematic picture of this, where here we draw all the edges, and here we only draw degree. Okay, so let's see. If you look at this picture itself, you can check. I mean, it's not easy to check, but you can check that there is no 3, 3. You know, 2 degree 3 being adjacent, and no 2 degree 3 being adjacent to the same degree 4. If you go from degree 3 to degree 3, you get at least 4, 4, 4. You cannot have, so this picture, you don't have this structure, you don't have this structure. But let's say sometime we decide, we are cutting this atom end, this atom on top. Okay, so let's say we cut this atom on top. Okay? Cut this on top, then we are getting this. And then this becomes degree 3. Well, notice that here in the bottom layer, we are having the fixed ends from both from top, from above, and from below. But now this is not a problem because we are going to do this greedy algorithm, and then we can always avoid the bad degree 2 as long as they are contained in the 3, 3. Okay, so let's look at this. Okay, so if you look at this picture, now you see this is now this is a 3, 4, 3. Okay, so 3 connected to 4 connected to 3. And this picture is like this connected to this connected to this. So let's remove it. Okay, so we get a 3, 4, 3. Let's remove it. 3, 4, 3. This is the definition here. So we remove it. Once we remove it, so you see this thing becomes degree 3. And this thing becomes degree 3. Okay, so in the picture here, you just remove everything here. And then you get a fixed end. Okay, so this is what we're doing NP. And then next, okay, so next you look at this, you have a 3, 4, 3 here. So you can just completely remove it. You get another 3, 4, 3. And this is 3, 4, 3. 3, 4, 3. Nothing. Okay, and then we have this. Again, you see this. You have a 3, 3 here. This is a degree 3, degree 3. So you can remove it. Now you have a 3 here. Okay. And then okay, so that means you remove this. So this is a fixed end. This fixed end. And now you have this is 3, 3. Remove it. And then in the empty, you're left with this. Okay, so that's that you are done with whatever you need for the greedy algorithm empty, and then you go back. Now you see in this case you have a big gain. You have a 4 good component. So this is good, and this 3, 4, 3 you can divide into a 3 and another 3, 3, which is also good. So in any case, you're getting a lot of good components before you go back. So this is what we mean by a greedy algorithm in NP, that each time you do anything, you're guaranteed to have a gain. And this is, of course, is a good thing. Essentially, any atom in NP that is connected to something, will contribute to the gain, and eventually this number of gain will be comparable to the number of UD connections rho, because any UD connection is involved in it. Okay? So,
sorry.
Yes?
For using the gradient algorithm, you may have different weights for different configurations.
Different, what?
Weight, for example.
Will be different. We only have this and this. Yeah, so so this will gain you some constant power. This will also gain you some constant power, but you will only have two cases. So no matter what, you're getting a constant kind of for each 3 atoms you cut, and then the power, the exact power is not that important. So just as long as it's a positive constant, it's okay.
I mean, some kind of trees should be preferred, right? In some sense.
Well, for these two, you don't need to have any preference because you only have 2 cases. Like this case, you gain like 1/2 power. This case, you gain 1/4 power. But it doesn't matter. You just imagine you gain 1/4 power in each case, and then it's fine. Of course, in the algorithm, we do prefer this one to this one, but for another reason. Okay. Okay. So then this is the greedy algorithm. So let me tell you a few things about this.
So when you perform the greedy algorithm in MD, for example, when you cut 3 or 3 for 3,
Yes.
You just sweep from above to.
No, you don't. There is no above and below here. You just whenever you see a 3 in any place, you just remove it.
But would that produce any like true?
Okay, so the thing is that you may have a fixed ends from both top and bottom, but as long as they don't occur in the degree 2 thing, as long as they occur in the degree 3 thing, that's still fine. Okay, so yeah, this is a good point. But good remark. For molecules with both above and below fixed ends, so this is not allowed. But if you have a 3, let's say this, so you have this is allowed. The reason is that if you have this, if you really integrate the delta function associated with this atom, you're getting a singularity because for these fixed ends, these are parameters. You're getting a kind of a delta function of the parameters, which is not allowed. But in here, you're integrating at 2 atoms. So if you integrate at one of the atoms, you'll get a delta singularity, but this delta singularity is again kind of resolved by putting it inside another integral. If you integrate the delta singularity, it gets into a bounded function, and then it is resolved. Okay, so as long as this thing, you get a singularity, but this thing is that since you have one more atom in this case, this allows you to resolve the singularity and still get a bounded function of output, which is this bound of I of this molecule is still bounded. Okay, so this is a very important point. I mean, in practice, it's much more complicated than that because this thing, it doesn't have a delta singularity, but it still has some denominators being singular. And then you need to insert some cutoff, ensuring these denominators are bounded below. And these are what we call the non-degenerate case, and there are also degenerate cases where you need to do something else. But schematically, this is what happens. Okay. So let me say something about this overall algorithm. So the greedy algorithm in NP ensures that each UD connection, well, let's say at least each half of the UD connection is definitely contributing 1 3 components. And so we get the number of 3 is bigger than rho. which is very good, but remember we are not finished yet because as a prize of allowing us to do the greedy algorithm in MD, we are doing a very naive algorithm in MU where we always choose the lowest. Okay, so this is something you can show that if you don't do this, then you cannot do the greedy algorithm in MD, otherwise you're going to have something bad in MU. But we are doing this naive. So basically, if you remember like yesterday when we introduced the naive algorithm, we say it's very naive. It doesn't work in most cases, but it's very robust in the sense that it allows you to do this very kind of greedy thing in MD, and it still kind of preserve the multiplicity in MU. Okay. However, we still may have degree 4, due to these naive, these naive. What about the naive in MU? Do we lose too many degree 4? Okay, so this I think is the nicest part of our proof, is that the number of degree 4s you lose is precisely this mu, which we assume to be small. Remember, this mu is the number of components of x, which we assume to be small in the dichotomy. So let me show you. However, so why is this? Let us again assume the top layer MU is a monotonic chain. In general case, again, you consider the different branches or trees, which is more complicated. But let's just assume that assume MU is a monotonic chain. Then what happens is that there are those points in X and those points not in X. Again, X has some components, so this is in X, and this is not in X, and this is in X, and this is not in X, and this is in XC. Okay? So when you do a naive up algorithm, each time you choose the lowest element in X. So each time you choose the lowest element in X, so you choose this one in X. Okay? When you cut this may have degree 4. Fine. So this may lose. This may degree 4. But then after you cut this, this, if you zoom out this piece, you're having a, like a point in, let's say in X, this in X, and then you have this, and then you have this, and you have this, and so on. So everything here is in X. If you cut this may be cut degree 4. But after this has been cut, you are going to have a fixed end here. And then next atom in X is next lowest is this one. This will not be cut as degree 4, this will have degree 3. Okay? And then once you cut this, you get a fixed end here, and this will not be cut degree 4. This will still be cut degree 3, and so on. So you see, for each segment here, which is each component of X, you only get 1 degree 4 in this, even when you do this naive algorithm, and the total loss caused by degree 4s is bounded by a constant multiple of the number of components of X, and precisely we're assuming this number of components of X is sufficiently small by this dichotomy. Okay, so you see this is a nice thing about this dichotomy, that this same quantity mu, which is the number of components of X, plays 2 completely different roles In the case 2, we are first cutting everything MB, and then this X plays a role of the number of components of the set of degree 3 atoms, and then this is we are good if this thing is big because we can gain. This can translate into the source of gain. However, in this final case, when you do this naive algorithm, this number of components X exactly translates into the number of loss, because for each component we are losing 1 degree 4, and this exactly translates into the source of loss. So if this mu is big, we do the previous thing. We get a gain which is proportional to mu, and we are good. And if mu is small, we do this latter thing, and then we get this gain kind of automatically, but then we are having a loss, but the loss in that case is also comparable to mu, and we have assumed mu is sufficiently small. Okay? And then this way we get some. Do I have? Okay. And this way we get some. Okay, so this we get some. Precisely because of this. So let me show an example, how this works in case 3. It's a bit complicated, but let's try to work it out to see how exactly, how to understand the steps of the algorithm. Okay, so let's draw this here. Okay, so we have so let me draw a slightly different one. We let this straight and this connected. What we do here, what is X? So in this case, X is everything. Everything above is the X. Everything above has a connection with so everything is in X. So let's say we start by cutting the lowest atom here, which is this one. We start by cutting this one. Okay? Cut this one. Well, let's say we keep the fixed ends just to. Okay? So the thing we do here is that every time we keep track of what happens in MD in the lower layer. Okay? So otherwise we just keep cutting the lowest. Okay, so in this case, this is degree 3 and everything else is still degree 4, so there is no such structure. So then we keep cutting next. We keep cutting, which is the next lowest in X, which is this one. So in the beginning we have degree 4, but then we have degree 3. Okay, this guy has degree 3. Okay, so let's say we cut this. So there is a fixed end here, and then there's a fixed end. Now you see this guy becomes degree 3, this guy becomes degree 3, and this degree 4, and then we are getting a 3-4-3 structure. So we do this and so we keep cutting this. Everything. Okay? Okay, now this also has a fixed end. Fine. again, at this time there is no other structure. This is degree 3, everything else is degree 4. So fine, we just go back to MU, go to the top layer. Now we cut the lowest, this is lowest, and this has degree 2. I mean, degree 2 is fine, it's allowed, as long as we preserve the monotonicity in MU. This isn't a problem. Let's see, we cut this. Okay. And what we do, there's nothing happens in the lower layer. We just keep cutting the next lowest in MU. That is this one. Okay. Let's say we cut this, create a fixed end here, and then let's say we create another fixed end here. Okay. So at this time we're having a 3, 3. Okay, so this is degree 3, this is degree 3 because we, after cutting this, we create a 3, 3 MP, so then we remove it. Move it this way. Okay, so again, now there's nothing happens in MP. We cut the lowest, so the lowest and the MU again is degree 2, but this is fine. And again the lowest, which is this one. And then once we cut it, you already see the pattern. So now this is 3, 3 that happens. Remove it, and then you get and then you have degree 2, and you finally cut it to finish the whole picture. Okay, so you see what happens in this algorithm in the final case is that essentially you see in the progress just now, everything in the lower layer is cut as a part of 3, 3 or part of 3, 4, 3. And 3, 4, 3 you can easily cut into you have a 3, 4, 3. 3, 4, 3 is equal to, you cut this 3 plus, and then this becomes degree 3, so you have a 3, 3. So it's like a normal component plus a good component, but as long as you have good components, this whole thing is good. Okay, so everything below belongs to a 3, 3, 3 or 3, 4, 3, and then this is as many as a number of connections, and you are good. And what happens about top? You lose a one single degree 4 component in the beginning, and afterwards you don't lose anything. Everything is either degree 3 or degree 2 that happens in the top layer. Okay, and this demonstrates that the gain is really comparable to rho, while the loss is bounded by a constant multiple mu, and mu is assumed to be much less than rho by this assumption of dichotomy. And then these procedures allow us to get both inequalities. Okay, so let's summarize. Lambda 2 conditions. Case 1, lambda bigger than rho. We have to do up, which is this is a variant of up associated with these 2 conditions. Otherwise, we pretend case 2. Case 2, mu, then MP to case 3. Then we do this final procedure. So naive up. Plus greedy algorithm. And then clearly these 3 cases covers all possibilities, and then this allows us to get a good algorithm, so that we preserve monotonicity, we maximize the number of 3 threes, we minimize the number of degree 4s in each of the 3 cases, and then this proves this theorem concerning a 2-layer case, and then by this reduction procedure, this implies the same theorem for the multi-layer case with any finding many layers, and then this completes the estimate for the molecule for the molecule integrals, and this leads to the estimate for the equivalent bounds, and then this completes the whole thing. Yeah.
If you have any questions, just take your last time to ask Professor Deng. Okay, Professor Deng, could you make further comments or remarks for what's next?
Yeah, what's next? So there are many natural questions. So one thing I've been talking to people is the long range potential. The short range should be essentially similar. I mean, long range case, I think if you have the potential decays fast enough, we may have a chance of using similar methods. But if it decays like with a fixed polynomial, like with a not so high degree polynomial, it probably will need new ideas. And in that case, you have many simultaneous interactions, and then it's kind of getting close to the Landau equation. Landau equation is again pretty open, like even for short time. So this is one direction, which is I think is pretty important. And there are other directions, like easy directions, meaning you look at the fluctuations and other kind of things. There are also questions of how to get longer time. So the hope is that if you are close to Maxwellian, e to minus v squared over 2, we may get slightly better time. I mean, the idea is that you're still dividing your time intervals, and then you have the number of time intervals still has this absolute log bound, but then there may be a chance that the length of later interval can be get longer if your solution to Boltzmann is really close to Maxwellian. Then maybe there's a chance that the difference between these and Maxwellian is decaying. So maybe you can get longer time. Eventually, you can get longer time. This is not clear, but since people are asking, what if you are in the different scaling laws other than Boltzmann grads, can you get the fluid equation in that case? I mean, this might be something that's at least worth trying. I'm not sure if you can get to polynomial, but if you even replace a double log by a single log, that would probably be already something. So, and of course, like the case of not so smooth, not so strong solutions, what happens with that, and many other things. Of course, the boundary case. We chose not to do the boundary case because it's complicated to do, but okay, it's something that certainly can be asked. I think there are many things that can be asked.
What do you mean by longer time?
Yeah, because now the time is restricted to log n.
Okay.
So yeah, what happens like if it's even like a log of n or maybe even a polynomial of n? Well, yeah, I don't know if it's even true.
Could you also make some comments? Compare this result with your previous wave kinetic.
Yeah. So, okay, so for wave turbulence, basically, I mean, again, wave turbulence, there are also a lot of open problems in wave turbulence, like including the cross-linear equations and maybe the other thing. So, okay, so wave turbulence is like this. See, wave turbulence is like the kind of the 2s point, because the correlations, this corresponds to the s point densities in the Boltzmann. Because in the Boltzmann density is positive, but in the wave equation, this the wave function itself is not positive, only its square, its norm square is positive. So you have to take in 2s number of correlations to correspond to this. Okay, so there is one more step here. So there is one more parent steps. So this is something that makes a technical difference, between the wave turbulence and Boltzmann. So that this will lead to a number of factorial divergences and a lot of oscillator integrals. They'll need to do, and occasionally you even need to use some number theory results concerning these the distribution of these spaces and so on. So the calculation is much more complicated in the wave turbulence case. On the other hand, the Boltzmann is also the low density limit. In the words of Paul Rendy in his talk concerning the quantum Boltzmann. And wave turbulence is a weak interaction limit. So basically, in the wave turbulence, the density is a constant. So in our language, n is epsilon minus 3, and you are kind of scaling wise, you're kind of similar to lambda, but the argument is actually much easier. This basically leads to less kind of singularity in the integrals, and this leads to more singularity. So this is represented by all these delta functions that we see in the definition of this IN. And the fact that we have more singularities really implies that we really need to, in the wave turbulence setting, you do the same kind of cutting procedure, but in that case, the cutting can be made kind of pretty, can be defined in a pretty simple way. You do not need to respect this monotonicity, and you can allow even to cut a degree 1 atom and so on. And this is very kind of much easier. And in this case, because of this singularity, that you need to have a much more complicated cutting algorithm. So despite that, the main scheme of these two things are indeed pretty similar. You start with independence, and then in later time you want to get irreversibility. So instead of independence, you make these ansatz about the correlation. Then you can also define the same notion of cumulance. Okay, and then you find a particular ansatz for cumulance, and you keep keep going and prove these cumulants ansatz by induction, and then you finally try to estimate the size of these cumulants to close the whole proof, and this is turned into the pure combinatorial structures called molecules, and then these molecules, the integral or sum associated with molecules is is ascertained by this cutting process. So the difference here is that in here you need a much more complicated cutting process, while in here you need a much more sophisticated, let's say, calculation of oscillator angles. That's not.
So far you achieved the validity of the Boltzmann equation, at least the hard sphere and hard potential for So we are wondering, at least I'm wondering, could this approach can characterize quantitatively some property of the Boltzmann equation? For example, we know for Boltzmann equation, okay, no matter initially away from max reading, however, at a longer time, okay, time goes to infinity, so will approach to the equilibrium, no matter what kind of a rate, okay, exponential or polynomial. We are wondering if now we have a more powerful, okay, microscopic point of view, can we characterize more quantitatively how, from the point of view of a microscopy, how this solution approach to this max reading?
Yeah, this is certainly a possible point. Like once you have validity of the approximation, you can try to develop some properties of the particle system to see like whether this says something about the densities and for a long time. But this certainly potentially can be done. There is a chance that this can be done, but we are not doing it in this work, and maybe it's something we'll think about in the future.
Any further questions?
I have one more question. So it seems in this cutting algorithm, so in the whole space case, the analysis doesn't depend on dimension.
Doesn't?
Yeah, but for the torus case, you do need the dimension.
Okay, so torus case is like this. Okay, so first of all, the one of the integral estimate for the 3-3 depends on dimension. I mean, we are not presenting here because in torus case, you need to, for some reason, you need to gain more power somehow. You need to gain more power. We have more precise estimates for the 3-3 estimates, and in that case, depends on dimension, and also in the torus case, well, you see. This related to the error term estimate, which I'm not even mentioning in this talk. That basically you have, let's say you have 1 million recollisions, then you need to gain a definite power there. And in the RT case, we're using a result of this Borrego and collaborators in 1998. That so RT is like Q particles can collide. Let's say less than q to the q square times. They have some extra upper bound on these kind of number of collisions, while in torus it's not true. So you need to consider the case where in the torus they collide these many times, and then they transfer to another fundamental domain, and then they collide another these many times, and then you need to kind of gain something from the fact that you don't have this, but then you have something weaker kind of. On TD, I mean, I'll not describe what that something weaker is, but you have something weaker on TD, and this may also affect the algorithm. Actually, in the torus case, we have a kind of less efficient algorithm that, instead of gaining a power of d minus 1, we only gain a power of 2, and that requires d minus 1 to be less than or equal to 2, and let's say we're in 3. Okay.
So suppose you have some kind of boundary conditions. Suppose you have some like a reflection wall. So does that pose some kind of problem for your diagram?
I don't think there is a problem for the recollision case, but it may translate to a boundary condition for Boltzmann equation. I mean, that's what I believe, but the technical parts remains to be done.
So could you explain a little bit why the chain structure is representative enough? Because the branching seems like very complicated.
Yeah. So I'll tell you one example. How these chains. Let's say the last example. In the case of X has very few components. So if you are another chain, what happens is this. So everything has to be translated to a case of another chain, but I'll just show you one. So let's see. If you have X, if number of components of X is less than rho, okay? So if you have a chain, then then this is X, and this is X, okay? Then this is the number of component is mu, let's say, okay? Then the minimal point, the lowest point in X is mu. So number of and this is the key thing you are interested in, because this is the degree 4 you will lose. Okay, so and this is because if you have a chain, then each X is a segment, and each segment has only one lowest point. Now, what happens if you have a general tree? Let's say if you have an X. Remember, each point in X is going to have a connection downwards. So let's say you have a point X. Okay, it's going to have a connection downwards. Okay, which means it can have only one other child in X. So each point in X. Now, in general, each point in X has at most one child in X. And you can have two parents, fine, but it has at most one child in X because it's going to have one connection down. Okay, so what happens here is that this X, or each component of X, is going to have an upside down binary tree structure, like this, since everything is a tree. Okay, so the binary tree structure is not important, but the point is that, again, each component of X still has at most one lowest point. Still each component and then still the number of lowest points is less than mu, which is the number of components. Okay, so you see how this result you generalize in the tree case is something like this. But the other result they also generalize in the same way. But okay, so we'll not discuss that. Okay.
Actually, I have one more question. So in my mind, because in case 2 you are suggesting if you have many components, when you split them, you will gain something.
Yeah.
So I think naively one would think in case 3, you also want to split the components first and then apply your.
Well, but you don't have many components from beginning. Let's say you only have one component, then you cannot split them.
Oh, but I think the bad 4 comes from your component, right? So
Yeah. So let's say there is only one component. I mean, you need this argument to prove you only have one loss. But let's say you only have one component, mu is 1. Then you need to do this case.
So I'm just saying why you don't combine the part in case 2 to avoid less, to avoid bad.
Because mu is already small. Mu is like this number, or mu is 1, doesn't make a difference. Okay.
Yeah, if no questions, let's send Professor Deng Yue again. Let's send in particular